This lesson deals with the piece-by simulation of an inverting regulator and the analysis of a step-up regulator. You can find these notes in the ECE402 ebook in Chapter 8, starting on page 29. Here's another implementation done by Chetty using a 555 timer to do a inverting regulator. So here's our basic inverting regulator where I've got a switch, inductor, power diode, capacitor, and a load. And just like before, we're going to use a smaller transistor here to essentially pull current or block it. So when the output of the timer is high, it saturates this transistor, we pull current through here, and we close the switch. The timer is set up as an A-stable, but we'll see that it actually doesn't stay very long in that mode, but is pulsed by the reset pin. Here too, I've got a connection to the reset pin. This transistor Q1 is cut off, and we just pull up to the power line, which is set with a Zener diode of 8.2 volts. Now what happens when the transistor saturates? Well, when it saturates, the voltage across here is around 0.6 volts. If current were to flow this way, then let's find the node voltage here. It's going to be equal to a minus the Zener voltage, minus the drop across the resistor, minus 0.6. And this is an 18 volt Zener. When this node voltage gets to be minus 18.6, current's going to be flowing in this direction, back through here, and that's going to cause this transistor to saturate, pull the reset pin low, and it's going to set the output low. Here's the file below. We're going to use a pulse to turn on the power supply because we have an oscillator. This time I had some trouble with convergence, and so I had to up the value of ITL4. This is the number of iterations at a single point during transient analysis. The default is 10. I had to bump it up to 20 to get it to work. Let's take a look at some of the output. This first graph is a plot of the output of the A-stable. This is the output of the timer. And you can see that it's oscillating over here, and then eventually becomes a series of pulses that are a little bit more spread out. You can see here the charging of the capacitor is doing the 2/3, 1/3, 2/3, 1/3. Eventually goes into some other kind of a cycle. This is the reset pin of the timer. You can see that it's high here, so that means that we are operating as an A-stable, but eventually then it pulls low, and that occurs when the output actually becomes negative enough. We're shooting for minus 18.6. This part of the waveform goes slightly negative. It's around minus 0.6. I didn't show the scale here to go negative, but this does dip down a little bit. And that's when the transistor again saturates. We go back to the picture here. This saturates, then this node voltage is going to be, say, roughly 0.1 and then minus 0.6. So it'll be slightly negative low side of that reset waveform. And then lastly, here's our output across the capacitor and the load. And you can see here there's a ripple and then eventually a steady state value. Let's take a look at some of the currents. First graph is the inductor current. You can see that it's doing some stuff here and eventually breaks into a pattern. Here's the current in the switch. Again, this is a PNP transistor, so we're looking at the negative of the collector current with our definition of 302. And 2 eventually goes into a steady state pattern. Likewise for the diode current, and eventually the capacitor current. Let's zoom in on some of these waveforms and see how they compare to what we derived last time. So our inductor current does look like a triangle. Peak here is 2.2 amps. Width here for T1 is 151 microseconds, and then integrating down, it's 113 microseconds, and then the remainder of this part of the cycle is 384. So the total period is the adding of those together. Here's the current in the switch. It follows the inductor current, and then it goes to 0. When the switch cuts off, the diode kicks in, and it follows the inductor current down, about the same peak value. And then the capacitor current is just shifted by I0, following that same pattern for the diode current. And when the diode current is 0, we just have the value of minus I out. Should have mentioned that the waveforms on the previous page look very much like what we did in the previous lecture on page 26. Here's the current in the load. See here it's got a little bit of ripple in it. Did a little larger scale here to make it look fairly flat, but the average value is about 189.7 milliamps. And then here's the output voltage, just zooming in on this part with the ripple in steady state. And it's going from minus 17.875 to minus 20.69. Let's predict the shape of this with our previous page. Look at the capacitor current again. We're going to integrate this waveform. So when we integrate this, we're going to get a negative parabola because we've got a ramp here. So the integral of it would be like t squared. And then I've got a constant here, and that's just going to be the integral of a constant, or just a ramp. And so we're going to see that on the plot here. Here's that parabola, and then here's the ramp that we generated. Let's grab some of the numbers from our simulation and compare them with our formulas. So our peak in the simulation was 2.2054 amps. The time that the switch is closed is 151 microseconds, and the total period is 648 microseconds. The average current is 189.7 milliamps, and the average voltage is just taking the two peaks, adding them together, and divide by 2, and that's going to be a minus 18.972. Lastly, the ripple is the difference of those two peaks, and it's a value of 2.1938. Using our formula for I0, we have 1/2 times Vn, which is 15, V out, which is 18.972. T1 was 151 microseconds, and the period was 648, and the peak current was 2.2054 amps. That's 203 milliamps. And that compares somewhat close to the value over here of 189. These are approximation formulas where we threw away the drop across the diode, and our output voltage is the square root of Vn of 15, the peak of 2.2054, a resistive load in this case of 100 ohms, T1 of 151 microseconds, and then a period of 648 microseconds. And that gives me an output voltage of 19.63. And again, we define this as a positive quantity, but that node voltage would be a minus 19.63. And here we're calculating a minus 18.97. And lastly, the ripple. We had this formula. So our capacitor was 47 microfarads. Peak was roughly 2.2. Average was 0.19. And then we've got the peak again of 2.2. We're going to square this numerator term, and then 15 divided by 18.972, and then times 151 micro. And that's 2.34 volts, and we measured 2.1938. So these formulas, again, they are based on Kirchhoff's laws and have to be satisfied at every instant of time. And so our controller needs to allow this to happen. And again, what's happening with the controller, let me go back to page 29 here, is starting out, this is going to start to oscillate and basically starts to charge up the inductor and eventually the capacitor. But as this voltage gets more and more negative, eventually this kicks in and it starts to pulse the reset pin and really change the function of the timer to just simply be a pulse of a certain width based upon the ripple that's showing over here. The feedback loop here is controlling what's going to happen out here. And Kirchhoff's laws have to be satisfied at every instant of time because they're based on conservation of energy and conservation of charge. And so it's forcing this to hover somewhere around minus 18.6 volts. Take a look at the next regulator, which is a step-up regulator on page 34. I forgot to mention one thing with the inverting regulator. I did look at the node voltage 10, which is the voltage across the inductor. It does have an average value of 0, but it did have a lot of ringing. It was a sine wave that had an exponential envelope around it, and the frequency of oscillation was around 320 kilohertz for this case. If we take the value of L and the values of the straight capacitance in the circuit, 1 over 2 pi squared of LC, you roughly get about 320 kilohertz. This frequency does cause a lot of noise and interference problems, and so sometimes we put very special enclosures around switch mode power supplies. The next regulator is called a step-up regulator, or a boost converter, and we use the word boost to mean bigger. So this is going to be an output voltage bigger than the input voltage. Close the switch initially, and the voltage across the inductor looks like this. The current is going to be equal to the integral of Vn divided by L1, and all that current circulates around here because we're shorting out the rest of the circuit. And now we open the circuit up. We have an open switch, and now the current continues to flow in this direction. It's going to flow in the capacitor and eventually into the load, building up a positive voltage across the load. But when a coil is discharging, the current comes out of the plus terminal, so the polarity flips on the inductor. So now this node voltage is bigger than the input voltage, and the output voltage is just one diode drop away. So as we open the switch, we dump the energy into the capacitor. Some goes in the load and begin to build up a voltage here. Close the switch again. We put all the voltage V in across here, charge up the coil, open it, discharge it into the capacitor. So if we keep doing this, eventually you'll reach some steady state voltage across the capacitor. And let's assume that we have a fairly constant voltage with a small ripple. The words are below here. I'll take a look at that on your own. Let's assume we're in steady state. Charge up the coil, we discharge it. There's a period of time where the current in the coil is 0, and then we repeat the cycle again. So we're starting out with a 0 initial condition. Calculate again the current in the coil. Going to be the voltage across the coil, which is Vn when the switch is closed. Integrate, say, from 0 to T, and we can evaluate this anywhere along the interval from 0 to T1. Bring out the Vn over L1. The integral of 1 d tau is just going to be tau, so upper limit minus the lower limit plus a 0 initial condition. So our peak value here would be that equation evaluated when t is equal to T1. When the inductor is charging, the switch is closed, so it's the same current. Of course, the diode was off when this was occurring, and we're assuming that the output voltage is fairly constant, and so we could think of it just as a straight line of an average value of I0. And then lastly, we can get the capacitor current. Let's go back to the schematic on the previous page. The capacitor current in this direction is going to be equal to this current plus this current. So it's going to be equal to I sub D1 minus I0. So in this case, I sub D1 was 0. I'm just going to subtract I0 from it. And go on to the next part of the cycle where we go from T1 to T2. All right, so it's going to be 1 over L1, the integral of the voltage across the coil, d tau plus the initial condition, which is going to be this value here of the peak current. Let's go find the voltage across the coil from the schematic when this occurs. Let's erase this here. Whoops. So the switch is open, so the voltage across the coil, and we're defining it in this direction, is going to be this node voltage, which is Vn, minus this node voltage, which is the diode drop, plus V out. So we're going to subtract this voltage and V out. And that's the expression right here. Let's again assume that this diode drop is small enough compared to Vn or V out. Assume this is small enough to neglect. If we do the equations, get a lot simpler. So I'm taking the integral now of Vn minus V0 d tau. This is just a constant, so pull that out. The integral of 1 d tau is going to be just tau, upper limit minus the lower limit, and then we have the peak value of current, which is equal to Vn over L1 times T1. Now we're arguing that V out is bigger than Vn, so this is going to be a negative number, and we'll be decreasing as time goes on. But eventually this will be equal to 0. Let's call that time T2 again. Let this equation equal to 0. So we have this first term and the second term. But now we're going to plug in T is equal to T2. Again, the L1s drop out. Put this on the other side of the equation as minus Vn times T1. We're going to divide that by Vn minus V out. Left with minus Vn T1 divided by the quantity Vn minus V0. Let me bring that minus sign inside here so I get V out minus Vn, because V out is going to be bigger than Vn. We have a V in the numerator and just T1 over here. Because the capacitor has an average current of 0, the average diode current is going to be equal to the average load current. Let's find that. What's the average diode current? Well, we've got the waveform over here. It's going to be area underneath this curve divided by the period. That's going to be 1/2 the base times the height. So T2 minus T1. The height is equal to I sub P. So the average value then is 1/2 the base times the height divided by the period. T2 minus T1 we have over here is equal to Vn divided by V out minus Vn times T1 divided by T, and then times I sub P. That'll be also our average output current, because the capacitor average current is 0. The average voltage out is equal to the average current out times R sub L. We have the equation for the average value of I out on the previous page, so we're just going to multiply that by R sub L. Let's cross multiply by this term, which is V out minus Vn. I'm left with 1/2 Vn, T1 over T, I sub P, R sub L. Now if you multiply this out, you get V out squared minus V out times Vn, and then minus this term on the other side of the equation. Now this looks like some x squared plus something times x plus something that doesn't multiply x, so we could use the quadratic formula. That's going to be equal to minus b, which is this term, plus or minus b squared, minus 4 times 1 times this quantity. So we'll get a plus, the 4 and the 2 become a 2, Vn, T1 over T, I sub P, R sub L. Now there are 2 roots here, but there's a V in here squared, and so this quantity is going to be bigger than this one, because I've got something added to it. So the negative term here must be the one we throw away. Pull out a Vn over 2, I got a 1 times that. Then you can pull out a Vn squared here and divide by 2, it's this term. And then in the radical here I'd have a 1, but if I pull out a Vn squared I got to put another 1 in here, so divide by Vn. 2 over Vn, T1 over T, I sub P, R sub L. So now this is my expression for V out. You can see what happens if you change the load, how I sub P is going to change and how T1 over T is going to change. This doesn't tell us the value of the output, just simply that this is a constraint on the output, and the controller must be able to allow this to happen. Now what about the efficiency? Well, I out was this expression. Our power out is the average value of the voltage times the current. But since we have basically a constant output, just take the product of the 2 DC values. So just taking this expression here and multiplying it by V out. The input power is going to be equal to 1 over T, the integral of the product of voltage and current. But since the input voltage is constant, you just pull that out, and we just have the definition then of the average current that's coming in, which is the inductor current. Broke this into two summations. Let's take a look at the previous page and let's see how that works. The area underneath this triangle, I broke up into two pieces. So I took 1/2 the base times the height, and then I took 1/2 the base times the height of this, and then of course this is 0. So let's take a look at that back on 36 again. So here's the first triangle, here's the second triangle. I have a relationship with T2 minus T1 is why I did that. Okay, so I have Vn divided by the period, 1/2 T1 times I sub P, and then I have 1/2 I sub P, and then T2 minus T1, we showed that was equal to Vn divided by V out minus Vn times T1. Pull out the 1/2, here's the T1, here's the I sub P, here's the 1/2, here's the I sub P, here's the T1. So what I'm left with is just 1 plus this term over here, which was Vn over V out minus Vn, and if I then add 1 to that, with a common denominator of V out minus Vn, that would give me V out minus Vn. These cancel, and I get 1/2 T1 over T, Vn multiplied by V out, divided by V out minus Vn. But that expression is exactly the same expression as the power that's going out. So my efficiency, again, is 100%, but in reality it'd be less than that because I've neglected to drop across the diode, haven't allowed any calculations with the resistance of the coil or in the resistance of the switch. The actual efficiency, again, will be somewhere in the 90% range. These are very efficient circuits, and basically it's dropping the difference between the input and the output across the coil. Lastly, we can find the ripple like we did back on pages 17 and 18. And that's the integral of the capacitor voltage when the capacitor current passes through 0. And that was again T3 and T1, just like it was in the last case. So we're going to get the difference of the integrals, and so that's going to be 1 over C1 integral from T1 to T3 of I sub C1. Let's go back to page 35. Find the area underneath the curve, so it's going to be T3 minus T1. And then the difference of this and this, which is going to be I sub P minus I0. And then times 1/2. So 1/2 the base times the height, and then dividing that by C1. That'll be a ripple voltage. But we don't have an expression for T3 minus T1. But we do have an expression for T2 minus T1. So we can again use similar triangles. The ratio of this height, which is just equal to I sub P minus I0 plus I0, divided by T2 minus T1. That has to be the same relationship as this height, which would be I sub P minus I0 divided by T3 minus T1. Go back to page 37. So that's an expression we just did. We're going to solve for T3 minus T1. So I have 1 over 2 C1, and then I have I sub P minus I0, which is this term here, and then T3 minus T1 will be solving this equation, which is going to be I sub P minus I0 times T2 minus T1 divided by I sub P. Same term, so I'm going to square that. And then the term T2 minus T1 we showed was equal to Vn divided by V out minus Vn times T1. You can see that C1, as I increase it, I'll reduce the ripple. Now it turns out for this particular case, Chetty, that had done our two previous designs, didn't publish any article that constructed this particular circuit using a 555 timer. Can you figure that out? And this was a presentation of the piece-by simulation of our inverting regulator, and also an explanation of how a step-up or boost converter works.